There we go. So this is example 4.6 from Potter's book. And in this example, we are given a small pump system where we have a pump that receives fluid through an inlet pipe and then pumps it to an outlet pipe, which is at a higher elevation. We have our little pump, and I'm going to try to see if I can explain what's happening. Fluid travels into the inlet pipe, then gets pumped all the way up to the outlet pipe. Now, we know a couple of things about this pump system. First, the difference in elevation between the outlet pipe and the inlet pipe is 20 centimeters. And at the inlet pipe and the outlet pipe, we have pressure readers, pressure gauges. Now, these pressure gauges give us a pressure of 200 kilopascal at the inlet and 600 kilopascal at the outlet. Now, we're told that the flow rate, right, the flow rate at which this pump is operating is 0.2 cubic meters per second. Okay. We are also told that the two pipes, the inlet and outlet pipes, have the same diameter. Okay, so we don't really know what the diameter is, but we know that it's the same. And I'm just going to call it D. And whatever it is, what we know is that it's the same. Now the question is, right, what is the required power for this pump in kilowatts? In other words, how much power does this pump require in kilowatts? So how do we start? Well, think of it this way. If we're asked about power, your mind should automatically go to energy. Okay? You think, we're asked how much power does a pump require? We're asked anything actually related to power. Power is work over time. Then you should think energy equation. Okay? So what I will do, and the way I solve the energy equation is actually a little bit different than how I solve other equations in this class. The energy equation, in my opinion, it's easiest to actually just write it down first, write down the whole equation first, and then start to work on it. Start to cancel out your terms and start to simplify your terms or do whatever adjustments you may need. So I'm going to start with my energy problem by writing down my energy equation. You can look it up, but if you don't, then I can just write it down here. I'm going to write the whole equation. You'll notice that after you get used to solving these types of problems, you don't really have to write the whole equation. You can start canceling out terms without even writing them. But because we are new to this topic, I'm going to write down the entire energy equation with all my terms. So this is my energy equation. I have a pressure term, velocity term, elevation term, pump term, pressure term, velocity term, elevation term, turbine term, and loss term. So my question is, the energy equation relates the pressures, the kinetic energy, and the potential energy from the inlet to the outlet of a control volume. So in this case, what's the inlet and what's the outlet of my control volume?
The inlet's to the left and the outlet's to the right.
Yeah, that's correct. So I'm just going to assign a number 1 to the left, assign number 2 to the right, so that they coincide with my inlets and outlets in my energy equation. Okay? And then I start to look at my terms. And the fluid is water. I guess I should have said that. The fluid is water. There we go. Do I know the pressure at the inlet? Okay. And do I know the specific weight?
Yes.
Okay. Do I know this? Do I know the velocity at the inlet?
Yes.
Think? What's the velocity at the inlet?
Okay, I'm actually not sure.
All right. Let's see. Somebody else. What do you think?
I would think you could solve for it using the flow equation, but you don't know the area because of the diameter. So.
All right. So for now, let's just say we don't know it. Do I know my elevation at the inlet? And I'm just gonna help you here. Elevation is really based on your own datum, right? Because notice that what we care about is the elevation difference. So you can just set a datum. So I can say that I know the elevation. Is there a pump in the system? I'm not saying if I know it, but is there a pump in the system? Well, yes. The entire problem is a pump problem. Okay. Lauren, do I know the pressure at the outlet?
Yeah,
Okay, cool. Do I know the velocity at the outlet?
I would say no.
Back to Shannon. We don't know the velocity at the inlet. We don't know the velocity at the outlet, but we do know that the diameters in both pipes are the same. We do know that the flow rate is constant through the system, Shannon. So what does that tell us about our velocities?
The velocities have to be the same as well.
Okay, so can we just cancel them out of this equation?
Yes.
Okay, so regardless of what they are, what we know is that they're both the same, so we're going to cancel them out. Good. Do I know my elevation? Yes. Is there a turbine in the system?
No.
All right. And then because our entire control volume is inside this pump, we're not going to consider losses in this system. So what I'm trying to get at with this step is not to ask you questions, right? I know that you know that we know the elevation, but I think it's important to write down this equation and then just start canceling out everything we don't need, because it actually makes our equation a lot easier to manage. Because now, look at what we're left with. We're left with a pressure term, potential term, pump term, and at the outlet, we're left with a pressure term and potential term. And that's about it. So from this point on, I think it's pretty easy to grasp what we're trying to look for, right? We want to calculate the power required by the pump. Okay, so which of these terms do you think will relate to the power required by the pump? Not that it's the power, but that it relates to that power.
HP.
Yeah, so that's what we want to find. So we're going to find HP, and we get that the pump head in the system is equal to the difference in pressures over the specific weight. And we get plus the difference in elevations. At this point, I think we all know how to plug numbers into our equations. We get our difference in pressure, that's 600 kilopascal. And I'm going to write the units because I want to make sure that we get our units right. Minus 200 kilopascal over the specific weight of water. Now we don't know, or we're not given a specific weight, but we know that it's water, right? So what's the specific weight of water? 9,810 newtons per cubic meters. But here's where I want everyone to be careful. These are kilopascal, right? A kilopascal is equal to a kilonewton per meter squared. So if you're going to cancel out units with your specific weight, notice that your specific weight has to be in kilonewton terms. So it won't be 9,810. What would the specific weight be then?
$9.81.
Yep. Kilonewtons per cubic meters. And then I have my difference in elevation. Z2 minus Z1, we know that the difference in elevation is simply 20 centimeters. 20 centimeters is 0.2 meters. So we can now calculate our pump head. If you plug those numbers into your calculator, we will get a pump head of, I'm not sure, let me try to figure out. We get 600 minus 200. I shouldn't really have to plug that into my calculator. Divided by 9.81 plus 0.2 meters. I get 40.97. You can run the 241 meters. Can somebody confirm that number?
That's what I got.
Okay, so we get 41 meters, but that's not what this problem asks us. I mean, that's part of it, but we want the power required by the pump, not the pump head. So here we go back to how we derived this equation. If you remember, we originally started with an equation where everything was in dimensions of energy. But we said that we want to deal with dimensions of length. And in order to deal with dimensions of length, we took the entire energy equation and we divided it by mass flux times gravity. And we defined the pump head term, we had defined it as the pump power divided by mass flux times gravity. That is the pump power in length terms. So this was from our derivation of the energy equation. So from this equation, we get, right, that the pump power, that is the power required by the pump, should be equal to the pump head times mass flux times gravity. Now we don't have mass flux, but what do we have that can help us calculate mass flux?
Flow.
That's true. We have the flow rate, so we get that the pump power is equal to the pump head times density times flow rate. This is the mass flux times gravity. Now, just as a side note, you will sometimes see the pump power equation written as pump head times flow rate times specific weight. But you should know that the reason the equation is sometimes written this way is because specific weight is simply density times gravity. So both forms work. So now let's just go ahead and find our pump power. Our pump power is equal to pump head. We're going to use the more commonly used form times flow rate times specific weight of water. My pump head is 41 meters. My flow rate is 0.2 cubic meters per second. And my specific weight, the specific weight of water is, and here again, we want to make sure our units are right. So because I already started using kilonewtons, I'm going to use kilonewtons again. So 9.81 kilonewtons per cubic meters. So we plug all those numbers. Let's see what that will give us. Let's see, I have 41 times 0.2 times 9.81. That gives me 80.4. Can somebody please confirm that number?
It's right. I got it.
Okay. So we got 80.4. Priscilla, I'm going to go back to you. What are the units?
It's kilonewtons meters per second. Right? Because the meters and the other meters cubed cancel out.
Yep. I'm going to help you out here. A Newton times a meter is a joule. So kilonewton times meter is a kilojoule.
Second, or kilojoules. Yeah.
But I'm going to help you even more. A joule per second is a watt. So a kilojoule per second is a?
Oh, so it's a kilowatt.
That's correct. So the answer would be 80.4 kilowatts. That is the power required by this pump. I think this is a good example because it actually forces us to use the equation and a little bit more on the side. Wow, we're almost out of time. So yeah, this is an example for pump, for energy equation applied to pumps.